Good evening, everyone. Waiting for others to join in. What's going on in school in Kormangla? What is happening? (2D) circular motion. All of you able to pick up, right? Whatever is happening in school. Laws of motion they started. That's little faster than what I thought. Laws of motion, though it is removed from your curriculum, they're still teaching it. Isn't it removed? Momentum. So they are only teaching momentum in laws of motion, or they're teaching everything? Any idea? No clue. Okay, anyways, so are you able to see that we have done these chapters in much greater detail and in a vast coverage we have done than what is there in your school curriculum, what is going on in your school? Are you able to appreciate that, or it is exactly the same way? Okay. All right, guys. So I think someone asked one doubt in the group. I could not reply. So we'll start with that question only, right? And moreover, there are still few more to join in. Why you guys join little late? You could have joined in time. Anirudh Sriram, are you from Mysore? Anirudh Sriram. Am I audible, Anirudh? Is this your first class, Anirudh? Can't hear you. Am I audible? Are you guys able to hear me, everyone? Okay, all right. Anyways, others will join maybe a little late. So I think this was the doubt. Let me put it over here. This. Oh, it got deleted, is it? This is the doubt, right? You can see this question. All of you, can you try attempting this? Then we will discuss it, okay? And once we are done with this question, we will then start fresh chapter, work by energy, okay? All of you, try attempting this. Just draw the freebird diagram. All of you, draw the freebird diagram. First, see, I'm not looking at answer, okay? You just draw the freebird diagram and write down the equations. That's all. Nothing else. Let me know once you're done with the freebird diagram. Okay. There are three masses which are moving. M, 5M and 2M. All three are moving. Okay. M and 2M. First, let us draw the freebird diagram of this. Are you guys done with M and 2M freebird diagram? Everyone? Let me know once you're done with M and 2M freebird diagram. All of you. Pradyun, done? Okay. On capital M, Rubav, what are the forces on capital M? Which direction? Tell me quickly. Okay, fatafat. Capital M, forces. G is a force. Is G a force? Rubav? Is G a force? Mg. Mg down. Then normal reaction up. What else? What else? Tension which direction? Tension left hand side or right hand side? Tension left hand side. Tension will pull, right? 2m similarly will have a gravity force 2mg, and there will be tension. Now this tension will be same as this or different? This one. What do you think? Everyone. This tension, will it be same as this or different? Same string, same tension, like this. Okay. Now, is the acceleration of capital M same as 2m? Suppose capital M has an acceleration this way of, let's say, a1. Okay. Now, will 2m go down with the same acceleration, or we don't know what is the acceleration? Acceleration of 2m will it be same or different? See, capital M is, sorry, this 5m is moving. Are you getting it? 5m is moving. Same as they are connected. Are you sure? Okay, let's assume it is A2. For time being, since there is a, this thing, we can assume it to be A2. Let us draw the freebird diagram of the 5m. Now this is 5m. What about friction? Read the question, Ansh. You haven't even read the question. How can you solve it? 5m. So 5mg downwards, right? What else? 5mg down. What else? Tell me the forces, other forces. Normal reaction from capital M, right? So there will be a normal, this is the pair of the force. This is the pair of this force, isn't it? Then what else? Any other force? tension, okay. From the ground also there is a normal reaction. Correct. From ground there will be a normal reaction N1. Now, will there be tension acting on capital M or not? Will there be a tension? Can there be a tension force from the string on 5M? Or before that, tell me a basic thing. Can I remove this pulley from the mass? Or I should not be removing it? Should I remove it or I should not be removing it? I should not remove it because the pulley is a part of 5M. It is fixed on it. So pulley remains as it is, like that. So tension will be which direction? Tell me direction of tensions, everyone. Tell me. On the right, on the left. How on the left? String is going over like this. So tension will try to pull it this way. So this is T, isn't it? Right? So now clearly 5M will be moving in this way. Let's say it is A3. Okay. Now let us write down the equations. What about other pulley? Sorry, I forgot that. Sorry. There is other pulley as well. This one. Good. There is this pulley which will have a tension this way, T, and there is a tension that way, T. Okay, let's say acceleration is that A3. Okay. Now, all of you just go through with the free body diagram of the three masses. Tell me, is there any doubt? All of you just go through it once. Now, 2M, there has to be a contact actually, because yes, there is a see in the figure, it doesn't show that there is a contact. But if there is no contact, 2M cannot move forward. What happens is when 5M moves forward like this, 5M will push 2M and 2M will start moving. So there will be a contact. On the diagram, it is not getting represented. So there is a normal reaction from here also. Okay. This normal reaction is different. I'm sorry. That is N only. And yes, this is N. This one is N1. We can call this as N2. So its pair will be where? All of you understand that there will be N2 force on 2M. Everyone understood this? Please type in. There will be an N2 force. 5M will push 2M. All of you able to understand that? Right? Now, the pair of N2 is where? Pair of N2, which direction and which? Pair of N2 on the 5M. Okay, yes, pair of N2 on 5M like this. So this is the normal reaction from 2M on 5M. Every force has an equal and opposite force, Newton's third law, right? So that is why this is the pair. Okay, can you repeat why it has to be a contact? Can you imagine 2M moving forward with 5M without 5M touching 2M? Can you imagine it? Just imagine like it is in the air. You imagine that the setup is there. Now 5M is moving like this. Until somebody will push 2M forward, 2M will not move with 5M. 5M is going forward. So when it is going forward, it will definitely touch 2M. Okay. And once there is a contact, 5M will push 2M and move 2M along with it. Clear? So basically 2M will have an acceleration this way also. And this acceleration will be equal to that acceleration, because both 2m and 5m are moving right hand side together. Clear? Everyone is able to understand all these free body diagrams? Go through it once, all of you. If there is any doubt, quickly type in. These are the free body diagrams. No doubts? I'm assuming, Sitij, I'm assuming. One direction you have to assume. Y direction, Y is the acceleration of capital M in opposite direction. Capital M, horizontally, what force is acting? Ansh, horizontally, only one force is acting, tension on the left hand side. So total force is on the left hand side. So acceleration should be on the left hand side. There is no other force. So for capital M, there is no ambiguity. Isn't saying that body is already moving. Which body you're talking about? Which body? Sir, 5m. Find the initial acceleration of wedge of mass 5m. I'm finding acceleration. Acceleration can come immediately. Okay? Immediately, as soon as you leave it, acceleration will come because net force is not zero. Any other doubt on the free body diagram? No? No doubts? All right. For capital M, what are the equations? Vertical direction, what is the equation? N minus mg is equal to what? Everyone? N minus mg for capital M is equal to 0. Very good. On it horizontally, tension T is equal to M into A1. Okay, so these are the two equations for the capital M. Okay, these are two equations for capital M. Now for 2M, okay, for 2M, vertically, what will be the equation, everyone? Vertical direction, tell me the equation. T minus 2mg is 0, okay? Others? T minus 2mg is 2m into A2, okay? 2mg minus T is 2m into A2, or T minus 2mg is m into A2? First of all, mass is 2m. You have to write T minus 2mg is equal to 2m into A2, or 2mg minus T is equal to 2m into A2. Which one is correct? Net force in the direction of acceleration is what? 2mg minus T. This is the net force in the direction of acceleration. This is equal to 2m into A2. Okay. By the way, this question is, you can say, advanced level. Okay. This is not something from which you can start learning the chapter. I'm assuming that you guys are done with the basic problem practice and you guys are done with the laws of motion chapter theory. Okay, then only you will understand it. So if you are joining in between or you haven't done it properly, laws of motion chapter, it will be difficult for you. Okay, you can't jump around here and there. You have to start with the basics. Anyways, horizontally, what will be the equation? Everyone, this is a vertical direction equation. Horizontal equation will be what? Horizontal force in the direction of acceleration is N2. N2 is equal to acceleration is how much? A3. So 2m into A3, right? So these are the two equations for 2m mass. Fine. Now coming to the 5m mass. Tell me, horizontally, what should I write? Horizontal direction, what will be the equation? Vertical direction will not write the equation. Only horizontal we are interested. In the direction of acceleration, net force is what? Are you able to see that this tension and this tension, they will cancel out? Okay. So net force is T, this T, okay, minus N2. Any other force horizontally? No, right? This is equal to 5m into A3. Okay, fine. Now, can you tell me one thing that, I'm saying 5m is going right hand side. 5m is going right hand side. That is what I'm claiming. Okay. Is it possible for 5m to go on the left hand side? I've assumed it to be right hand side, but can A3 be on the left hand side? Can N2 be more than T? Is it possible? Everyone? Is it possible for N2 to be more than T? Then net force will be negative. So acceleration will be negative as in the opposite direction. Is it possible? And if it is possible, if you say that it is possible, tell me, if 5m starts going on the left hand side, will there be a normal reaction between 5m and 2m? If 5m go on the left hand side, will there be a contact between 2m and 5m? No contact. So only force will be tension, and tension is again on the right hand side. Right? So that is the reason why 5m will always go on the right hand side only. Okay, there is no other option. All right. Now, since we are writing all the equations, for the heck of it, we'll write the vertical direction also. But vertical direction equation for 5m is useless. Can you tell me why it is useless, everyone? Vertical direction equation for 5m is not useful. The reason? It doesn't give info. क्या info चाहिए तेरे को? Huh? It won't move vertically. So what? Same relation. No. It gives you one extra equation. Okay. It gives you one extra equation, but one extra variable also. N1. And this, mute yourself. Who has joined? Anirudh. Sriram Chandran. Who is new today? Anirudh Sriram and Anirudh Sriram Chandran. Both are same? Looks like.
No, sir. I'm connected with another device. I've left the other device which I was using.
Okay. No problem. So, is this your first class? Are you joining first session? ठीक है, no problem. हाँ, चलो. So now vertical direction, if you write the equation, it will be n plus 5 mg. Everyone, n plus 5 mg. Okay, what else? Plus T. There's a tension also, this tension T. Okay, minus N1 is equal to 0. Okay, now here also you get the two equation, but I am saying the second equation is useless because it gives you an equation in which there is a new variable which is not there in any other equation. So basically one extra equation, but one extra variable also. So it will not be useful. So you need not be writing it anyways. Okay. Now how many variables are there? Counted. T, you have N, you have N1, N2, you have A1, A2, A3, right? How many? 7. Equations are 6. You need one more equation. What equation will be that, everyone? Six equations are there, but 7 variables are there. You need one more equation. How to get that? What will be that? No one knows? No one? It will be constrained motion equation, constraint relation. Okay, it will be a constraint relation. Fine. Now, constraint relation is a relation between A1, A2, and A3. So write down constraint equation. Tell me how to write the constraint equation. Look at this pulley. Okay, acceleration of this pulley is what? You have learned, right? You have learned it, that if there is a pulley, acceleration of pulley is AP, it will be A1 plus A2 by 2, right? Remember, right? Acceleration of pulley is what in this case? Acceleration of pulley is A3. The pulley is going this way with A3. Acceleration of this point is what? Acceleration of this part of the string. The upper part of the string is how much? A2. This is A2. Okay. So this one part is A2. And this one, with what acceleration this one is going? A2 is going this way. And it is going A1 that way. Right? So I can say that A3 is equal to A2 minus A1 by 2. They're in opposite direction. So that is why A1 is this way. A2 and A3 are in the right hand side direction. So from here, you will get 2 times of A3 is equal to A2 minus A1. Okay. So this is the constraint relation. Now all the equations are there and you have to solve them and you'll get the answer. Everybody understood? Type in quickly if there is any doubt. I have some net issues. What net issues, Aditya? Who asked this question, by the way? Who asked this doubt? Gurman. Gurman understood? I don't know why you're so worried. Huh? Why? One person is from out, probably. Anyways, one more question. Where it is? One more question you have sent me. Send me only or on the over the group you have sent? To me only. What is the number? Tell me phone number. I'll search it immediately. 9731 972. Okay, fine. Oh, semi-vertical angle, rest plane, a rubber ring requires a force. This one, increase in the radius of the ring. Okay, this question I have solved with HSR 11 people also. So the entire solution is recorded already. So I'll send you the solution over the group only. Don't worry about it. Okay, it is there. This question is little vague though. Okay, so I'll just give you a little bit of hint. When you stretch the ring like this, the force will be towards the radial direction, which is K times delta X. So probably how the ring is acting there, you might have the trouble. Okay, but I don't want to discuss it right now because it is little ambiguous also, but I'll send you the solution. Okay. Anyways, so let us start the chapter, a new chapter. How confident are you on a scale of, let's say 1 to 10, how confident you are with laws of motion chapter? First, you tell me school level. School level, how confident you are, 1 to 10. 10, JEE mains. JEE mains level, what confidence you have? School is 9. School is 9 only, not 10. 9.55. Arnav says 9.55. So he is accurate up to second decimal place. Oro. Why not Arnav? Okay. Good. So good to see that you are realistic. You are not overestimating yourself. The moment you start overestimating yourself, a downfall starts. Okay. So never assume that you are 100%. Okay. All right. So my assessment is that you guys are, most of you, I'm saying in general, on an average, I'm saying, okay. On an average, I'm saying that JEE mains, you are up to 6 or 7. Okay. Advance, you barely started, and mains, and the school level, you can take care of it, 8 to 10. Okay. All right, guys. So let us start this chapter. Very, very nice chapter. You will love it. This chapter name is Work by Energy. Why I'm saying that you will enjoy this? Because first time, you don't have to worry about taking components. Work, power, energy. But at the same time, in physics, you'll see that everything is connected. So you will never be able to do well in this chapter if you are not good at laws of motion chapter. Okay. So the entire physics is like that. Entire physics. Leave the units and dimension chapter alone. After that, if you're not good at kinematics, forget about laws of motion. If you're not good at laws of motion, forget about work by energy. If you're not good at work by energy, forget about rigid body motion. If you're not good at rigid body, forget about JEE mains. Okay, so everything is connected. So that's the reason why everything is important here. Forget about physics. you can forget physics. Physics won't forget you. It will haunt you the moment you write some exam. Anyways, guys, let's proceed. This chapter is about work, power, and energy. Okay. Now, as crudely it is mentioned here, in this chapter, we'll be discussing 3 concepts only. Number 1 concept, work. Number 2 concept, power. Number 3 is energy. Okay, one by one we'll discuss it. Not only we'll discuss these concepts, we will also discuss how work and energy is connected. Okay, because having energy, let's say I have a lot of energy, or let's say if I let's say burn something, a lot of heat energy will be there. Heat energy can be generated very easily. But if you do not convert energy into work, that energy is useless. Just having energy doesn't mean that you have done the work. It is like, oh, I am very intelligent, I don't need to study. If you don't study, you'll anyway fail. Whether you are intelligent or not doesn't matter. Same way, having energy doesn't guarantee that you have done the work. Ultimately, work is important. What is the final outcome? Okay, so what we'll do is that we'll discuss one by one, all of them, because now you will have little bit of understanding of all these three concepts, but that understanding could be little philosophical in nature. Okay. So for example, work. Okay. Let's say, if I talk about whether work is done or not, many things will come in your head. Oh, assignment is there. If I do the assignment, my work for today is done. If I eat food, my work is done. If I play PUBG, my work is done. Okay, so different people have different meaning towards what is work. So that is philosophical. We need to define work with respect to mechanics. Okay, in physics, what is work? And once you define what is work, then we have to stick to it, stick to the definition, and then try to analyze every situation with it. Now, the way you define work in physics doesn't mean that work is that only. If I say work is force into displacement, okay, if I say that is work, and you do your assignment, your homework, force and displacement both are zero, doesn't mean that work is zero. It totally up to how you define it. Now, God hasn't come and told us that work definition should be this. God hasn't told us anything. God hasn't told us what is kinetic energy. God hasn't told us what is force, whether force is equal to mass and acceleration. It is our own creation. We have assumed that let us call force is equal to mass and acceleration. Let us call kinetic energy as half mv square. The same way, we are going to arrive at the formula for the work. Okay, and then we will stick to it. But the way you define the work should be based out of observation. Because, for example, the force definition, force is equal to mass and acceleration. Clearly, based on observation, you have seen that if mass is more, your effort or your force has to be more. So you cannot have force is equal to acceleration divided by mass. That is against the observation. You could have force is equal to m square into a to the power 3 by 2. But that is complicated. So we have used the simplest possible. So same way, we need to define work. Okay. Now, when I say work is done, philosophically, what comes in your mind? Like, how can you explain it? If anyone comes to you and say work is done, work done, what comes in your mind? Anything, whatever comes in your mind. Tell me. Displacement has occurred. I mean, if a little boy comes to you, a kid will come to you and say that work is done, does that thing will come in your mind that displacement has occurred? No, right? Okay, exam is over. Okay, what else? A particular task is over. What does it mean particular task is over? Particular task is over means what? Let us get into that. Does it mean that I have made a lot of effort? If somebody says that work is done, does it mean that lot of effort is made? Need not be or it should be? Need not be or it should be? Need not necessarily, right? Not necessarily. Because you have seen that sometimes you have to do little bit of, work and the outcome is big. Okay, sometimes all you have to do is to take a decision and the output will be big. All right. So definitely it is not about effort. Then what it is about? Particular task getting over. If it is not about how much effort you have made, then what it is about? Completion. Energy spent. Is energy spent? Does it mean that work is done? If you spend the energy, does it mean work is done? You can bang your head on the wall, your entire energy will be spent, but no work is done. Right? It means that something has changed. Right? Are you able to understand? Something is changed. Whatever was earlier whatever was happening earlier and whatever was a status quo has changed. If somebody says work is done, status quo has been changed. This is what it means. Okay. In mechanics, change means displacement. Okay. Change of position. Change means displacement. Fine. All right. So let us start with that basic understanding of the work. Write down the work is what we are talking about here first. The change in physics is referred as displacement. So work is definitely related to the displacement. Okay. Now, if displacement is very small, doesn't mean that work should be very, very small. Doesn't mean that if displacement is very less, doesn't mean that the person has done very less amount of work. Need not be, right? It need not be. Suppose I am displacing a 1 gram mass by 1 meter, and I am displacing, let's say 100 kg mass by 1 meter. There's a difference. When I'm displacing 100 kg against the friction, I have to do a lot of work, even though displacement is same. Okay. So in a way, it also depends upon how much effort is needed for the change. See, effort needed for the change and effort applied are two different things. Are you getting it? Applied effort may not be the effort needed. Or for example, if you are pushing the wall, wall doesn't move, the work done is 0. Okay. Are you getting it? But if you push the wall with great amount of force, you are like one of those superheroes, pushing it with great amount of force, and the wall displaces little bit, then you have done tremendous amount of work. Because force is very large. Even though displacement is less, force is very large. So, any of these two things, displacement or the effort, which is force, if any of these two things are 0, your work will be 0. It is like force is equal to mass times acceleration. If mass is 0, force is 0. If acceleration is 0, then also force is 0. But if acceleration is little bit and mass is huge, the force will also be large. But if acceleration is 0, even though the mass is very, very big, force will be, the force will be 0. Okay. The same way. Okay. So work should be related to both displacement and force. If any of these two things are 0, the work should be 0. Okay. Displacement is referred as S in physics. Force is referred as F. Okay. Right now we are only treating the magnitude of force and magnitude of displacement. Now work is referred by W. W. Do you know the SI unit of work? Anyone? SI unit of work? All of this, you know it already. Okay. I think, yeah, it is joules. SI unit is joules. I don't need to tell you these kind of things, but still, I'm not assuming that you have done this in class 9th, although you have done it, but I'm going right from the scratch. Okay. So work done, sometimes it is referred as like this, W dot D. Work done should be force into displacement. Okay. Magnitude of force into magnitude of displacement. This could be the value of the work done, the way we have discussed it. Okay. Now, if let's say assignment is given to you, and the way it happens nowadays, that you hand it over to your parents, your parent does the assignment, and you go to your school and tell that the work is done, assignment is done. Okay, but have you done it? No, your parents have done it, but work is done. Work is done, but you haven't done it. Okay, so asking about work done is meaningless in physics. What we should ask in physics is work done by which force? Work done by a force. Suppose assignment is done, and if I have to check, if I ask you what is the work done by you, how much assignment you have done, your answer should be nothing. So work done by you is 0, although work is done. Similarly, when I say work done, I have to say work done by a force. Work done by a force. Simply saying work done is meaningless. I have to say work done by mg, work done by friction, work done by normal reaction. Like this you have to speak. Okay. Now, when I say work done by a force, let us take an example. Suppose I am pushing a block like this. Like this I am pushing the block. Okay. But block is moving like this, perpendicular to my direction of push. Block has a displacement. But I am pushing the block like this. Block is going like that. Now tell me, the block is going like this. Is this movement because of my push? Is that movement because of my force? No, right? Because if I push it, it has to move in the direction of my force. But if it has no component in the direction of my force, the work done by my force or work done by me is 0. Okay, same thing here also. Now, why the object is going like this? Probably some other force is pushing it this way. Okay, so work done by this force is not 0, but work done by that force is 0. Okay, so multiple forces are doing work on a single mass, multiple forces. Some forces work done will be 0, some forces work done will be positive, some other force the work done will be negative. Okay, so depending on whose work done you are finding out, you have to check that way. Okay, so work done by a particular force is basically, write down, force into displacement in the direction of force. This should be appropriate definition. Okay, and this is what is accepted, that work done is force into displacement in the direction of force. Now let's see how we can elaborate it a little bit more. Let's say displacement is in this direction. This is displacement and this is force. This is a displacement vector. Let's call it as S. This is your force vector. Call it as F. This angle is theta. Now, what is the component or what is the displacement in the direction of force? Anyone? Component of displacement in the direction of force is what? Everyone, component of displacement in the direction of force. S cos theta, right? Component of any vector along a line that makes angle theta is vector times cos theta. Okay, so this will be equal to F, magnitude of F into magnitude of S into cos of theta. Like this you can write. Okay, and this thing, it is very important to learn this also. Same thing can be written as F cos theta into S. Now, what is F cos theta, everyone? What is this bracket term? S cos theta is a displacement in the direction of force. What is F cos theta? What is F cos theta? If S cos theta is displacement in the direction of force, correct. It is force in the direction of the displacement, okay, multiplied by the displacement. Okay, so whether you write force into displacement in the direction of force or displacement into force in the direction of displacement, both will give you the same answer. Okay, and you'll see when you solve numericals, sometimes this definition is easier to use and sometimes that definition is easier to use. Okay, now can I write the definition of work done in a vector form, everyone? Can I write it like F dot S? Can I do that, everyone? Okay, so in a vector form, this is how you can write the work done definition. Clear? So we have defined the work done. No doubts, right? Now, what is the assumption here, all of you? The assumption is what? We have made one assumption, basic assumption throughout when we have defined it. Everyone? The assumption is the force is constant. Force is constant. Okay. Now, what if force is not constant? Then what we have to do? Okay. Let us see that as well. So let's say I draw a diagram for the case when force is constant. Okay. X-axis is the displacement in the direction of force and y-axis is the force. Okay. Force is constant. So this is how it will be. All right. So area of this graph represents what? Everyone? What does this area represent? This is the amount of force. This is the amount of displacement. What does area represent? F into S represents the work done. Okay. So the area is represented by the work done. So area in this case is work done. Okay. Now let's see over here. What if the force is variable? It is not constant. It is like this. Okay. Then what you will say about the area? What is the area? Everyone? If you take a small strip, a thin strip like this, for this thin strip, for which the displacement, okay, for which if I say this one, this displacement ds is a small displacement, okay. For this small displacement, can I say the force is constant? For this small displacement, can I assume force is constant? The displacement is so little, the variation in force is almost nil. So I can assume that force is constant, okay. So for the ds amount of displacement, okay, the small work done is what? Force at this location into ds, right? Force into ds. ds is, see, this x-axis is displacement in the direction of force. If you want to consider the actual displacement, it will be f dot ds. When you take dot product, automatically displacement in the direction of force will come in. This is the small work done for this thin strip. Now like that, you can have a thin strip over here as well. Okay. Over here also, the small work done is F dot ds. Now you can see that F is this much, the vertical height is F, ds is the width. So F dot ds is area of this strip. Like that, you can keep on considering small strips. You're finding small work done and add all of them, you'll get the total work done. So when you're finding the total work done, you're basically adding the areas. Okay, now, so I'm saying that work done is summation of all F dot ds. Now F is a continuous function, so the summation becomes integral. Integral of F dot ds. Like this. Getting it? If F is constant, F comes out of integral. Anyway, it will become F dot with integral ds. Integral ds is a total displacement. Okay. Right? So area of the graph for force and displacement curve. Displacement should be in the direction of force. Area will represent the total work done by that force. Whether force is constant or variable, it does not matter. Clear? Okay. Now let us continue with few cases of the work done. For constant force, I am talking about the work done is F into S into cos of theta. Okay, magnitude of force into magnitude of displacement into cos of theta. This is the work done. All right. So we'll be taking various cases and examples and see how the work done changes. Case number 1. F and S are same in all the cases. I'm only changing the theta. Okay. Case number 1, theta is 0. The work done will be simply force into displacement. Okay. It will be greater than 0. Positive work done. Tell me examples. Tell me examples of the work done here. Pushing a block. That you have to tell me which force and which block is there, multiple forces are there. Which force work done you're talking about? Everyone, tell me an example when the angle is 0. All of you. Someone is saying pushing a block like this. So you're applying a force like that. Block also goes in your direction of the force. So the angle is 0. Correct. When object is falling freely. So which force you're talking about the work done? mg. Correct. Gravitational force. So when an object is falling freely, the gravitational force is down and displacement is also down, right? So the angle between force and displacement is 0, and hence that is an example here. In fact, this is considered to be the most common and the obvious example. How it is 180, Ashok? Falling object angle is 180 between gravity and displacement. Think over it again. Gravity is down. Friction कहाँ से आ गया? Falling object, where is friction? This is S and this is your F. You're pulling the block and block goes that way. So this is like the most common example. Okay. All right. So this is the case number 1. Write down case number 2. Case number 2 is theta equals to 180 degrees. So the work done will be what? F into S into cos of 180, which is how much? Cos of 180 is how much? -1. So work done will be negative, isn't it? So this is again a very common case. Tell me. Example. Examples. Brakes, work done by friction on a car. No, friction on a car is forward direction if you don't know most of the time. Friction, if it is not there, you can't move the car. Give a simpler example, you know, day-to-day life example, just like you're given for case number 1. When you're pushing the block like this, there is a force for which the angle is 180 degrees. Which is that force? When you're pushing the block like that, there is a force for which angle is 180, which is what? Friction. Friction, right? You have a block like that. This block moves like this. Friction will be acting this way. So the angle is 180 degree between displacement and the friction, right? Friction is one of the force. Now, can you tell me, is the angle between friction and displacement will always be 180 degree? Will it be always 180 degree? No, right? Need not be. Okay. Many a times friction will be in the direction of the displacement. Example. What is that example? Anyone? Simple example. Ajit, look at this. This is a pen on my hand. When I'm moving like this, which direction the friction is on the pen? On the pen, which direction the friction is when I'm moving the hand forward like that? It is in the forward direction only. You remember the block kept on the truck is accelerating. On the block, friction is in the direction of acceleration only, right? So many times, friction and displacement, the angle could be 0 also. Okay. Many times displacement is 0. Many times angle is 180. Many times angle is 0. So do not ever assume that if friction is there, always work done will be negative. Okay. That is not true. Another example. Tell me some example related to ball in the air. Something like that, you tell me. No. Keep it simple. Very simple example. Ball moving upwards. When you throw a ball upwards, displacement is up. Gravity is down. Angle is 180. Okay. So even the gravity, at times, the angle is 180 degree and the work done by the gravity will be negative. Okay. So many examples are there. Do not force yourself to think that always this force, the work done will be positive. Always that force work done will be negative. All that is nonsensical. Never ever create such kind of rules in your head. Only thing which you remember is the formula for the work done. Other than that, everything else, you keep yourself open-minded, ready for anything. All right, so let's proceed. Case number 3. Angle is 90 degree. So the work done will be what, everyone? Work done is magnitude of force, magnitude of displacement into cos of 90 degrees. This is how much? Cos of 90 is 0. So work done is 0. Okay. Examples. Circular motion. Simple example there by simple example. Work done by normal reaction. So when I'm pushing a block like this, blocks goes forward. Normal reaction is in which direction? Which direction normal reaction is? Up. Is the angle between normal and displacement 90 degree? Normal reaction like this, displacement like that. You are pushing like this. This is your force. This is the displacement. This is the normal reaction. And this is the gravity. Is the angle between gravity and displacement also 90 degree? Right? So both normal reaction and gravity, in this case, the work done by them is 0. Work done by normal reaction and gravity in this case is 0 because angle is 90 degree. Work done by force is positive. And if there is a friction, work done by friction will be negative. Okay, I hope it is clear. Have you heard about that example in your class 9th where someone is carrying luggage on their head? The work done by that person will be 0. Have you heard about that? Arabi said that. Okay. Do you think it is true? Is a person not applying any force in the direction of displacement? Look at this. This guy is carrying something overhead and moving forward. Let's say acceleration is A. Do you think that person is not applying any force in the direction of displacement? If person is not applying any force on the luggage in forward direction, then what force is accelerating the luggage forward with him? There has to be some force. If you draw the free body diagram of the luggage, here are free body diagram. Okay, this is the free body diagram. mg is down, normal reaction up, and if this luggage is moving with the person, even this luggage has to accelerate with A. Otherwise, it will not accelerate. There has to be a force in the direction of acceleration. Okay, so there should be some friction. Okay, who is applying this friction? Who is applying? This guy. This guy is applying friction. Okay, if suppose friction is not there, then that person has to hold so that if friction is less, the person is pushing it while holding it. So the normal reaction is pushing it forward. So do you think work done is zero? No, the person is applying a force in the direction of the movement of the luggage if there is an acceleration. Okay, if acceleration is zero, then they don't need to apply any force. The constant velocity, everything will move forward, but that is not usually the case. Okay, so that's the reason why it is false to say that the work done by this person is zero. Work done by gravity is zero. Yes, gravity work done is zero, but you are assuming that person is not moving up and down. You are assuming that the person is moving in a horizontal floor. Okay, many things you are assuming when you say that work done by the person is zero, but in general, even gravity is doing work. Normal direction also does the work. Okay, but yes, idealistic case you can say. You know why I'm telling all of this? So that it opens your mind. As in, you should come out of all the assumptions. You should never make any assumptions. You should just treat the formula of the work done as it is and take it in a case-to-case basis. If it just stands, the work done is zero. Then work done is zero. Case number 4, all of you. How gravity is doing work? If suppose there's a staircase, this person moves up the ladder, then gravity is acting down, the displacement is up, so work done by gravity is negative. Correct. All of you, focus here. Case number 4, if theta is acute, theta is less than 90 degree. There are many cases like that. Okay. For this case, the work done is equal to F into S into cos of theta. And if it is acute angle, cos of theta will be positive and work done will be greater than zero. Okay. Case number 5. If theta is obtuse, greater than 90 degree, less than 180, then the work done is less than zero. Okay, so work done can be zero, work done can be greater than zero, work done can be less than zero. It could be anything. Okay, it could be anything. I hope it is clear to everyone. Shall we take up few questions now? This is the definition of work. Okay. Any doubts? Quickly. Repeat. क्या repeat करना है? What? Last case. If theta is obtuse, cos of that angle is less than zero. For greater than 90, cos of angle is less than zero, so work done is less than zero. In case 4, the verse is opposite direction when angle is acute, then work will be negative. Angle cannot be acute if it is in the other direction. What is this angle between? Angle between force and displacement. Okay, it will be like this. This kind of scenario is angle is acute. This kind of scenario, angle is obtuse. Angle is between force and displacement. In obtuse case, the component along the line of force will be in opposite direction. In acute angle case, the component is in the direction of the force. Okay, any other doubt? FST. Theta obtuse. No doubts. Okay. Fine. So that is about the work done. Let us take few questions and see if we have any difficulty. This is the force, okay, F. Mass is M. Coefficient of friction between the block and the ground is mu. Okay. This block moves forward by a distance of S. S. You need to find out the work done by all the forces. One by one, you list down all the forces and work done by all of them one by one. Like work done by force F is this, work done by gravity is this, like that you write down. Angle is 90, Oshik. You don't need to remember anything. Just the formula for work done is enough. Okay, so work done by the force. How much? F into S. Okay. Now, if you draw the free body diagram, what are the forces? Mg down, normal reaction up, friction back way, mu times normal reaction, like this. Okay. Work done by the friction is, sorry, force is F into S. Work done by the normal reaction, how much? Zero. Work done by gravity? Zero. Okay. Work done by the friction is how much? Minus of force of friction into S. The angle is 180 degrees. Friction is how much? Mu time normal reaction. Normal reaction is how much? Mg. Because N minus Mg is equal to 0. Simple question. All of you understood? Right? Oshik, you will see that in questions. Don't worry much about it, okay? Everybody else have to wait then. Don't wait for your doubts. So all of you, the moment you have a doubt, there only you should clear it up. Otherwise, everyone will have to wait, right? Everyone will have to wait. All right. So yes, Osha, you just keep on solving questions. You'll understand it. It is better to understand from numericals than somebody just telling you as theory. So this is the mass M. Okay. And can I? All right. So find out the work done by all forces in time t. In time t, how much is the work done by all the forces on this block? Coefficient of friction is mu. Okay. This block is sliding. Okay. This friction is not strong enough to hold it. The block is sliding. Block can slide. Done. Ansh is done. What is the first thing you have to find here? What is the first thing you should find? Acceleration. How the acceleration will help then? Finding acceleration then? After finding acceleration, you find the displacement. Right. You need to know what is the displacement, because in the formula for the work done, displacement is there. So first thing is, in time t, you have to find out how much it moves. Okay. All right. So let us draw the free body diagram. Clearly, this one is mg cos theta. You need to remember this. Okay. Along the incline, it is mg sin theta. Like these are the forces. Mu times normal reaction. This one is mg cos theta. This is the normal reaction. And this is mg sin theta. Acceleration is in this direction, along the incline. All right. So along the incline, net force is mg sin theta minus mu times normal reaction. This is equal to mass time acceleration, and normal reaction minus mg cos theta is 0. So normal reaction is mg cos theta. So acceleration, you'll get it as g times sine theta minus mu g cos theta when you substitute it over here. All right. Displacement, see, acceleration is constant. Displacement is ut plus half at square. U is 0, starts from rest. So this is a displacement. Displacement in the direction of the inclination. Okay. In the direction of the inclination, the displacement is half at square. Now, the work done by the normal direction is how much? Work done by normal direction, 0. Okay. Work done by the friction minus of mu times n into displacement, where displacement is this, you already found out. Work done by mg cos theta, how much? 0. Work done by mg sin theta is mg sin theta into s. So which formula you have used to find out the work done over here? By the gravity, what formula you have used? You have found out component of force in the direction of displacement into displacement. You haven't taken component of displacement here to find the work done by gravity. You have taken component of the gravity force and then multiplied that by the displacement. So second formula you have used here. Any doubts here? Anyone has any doubt? No doubts? I'll proceed. How S is half at square? By if acceleration is constant, S is equal to ut plus half at square, right? S equal to ut plus half at square. Okay. Again, I am cautioning you, our habit is in class 10th, our habit was that the moment one chapter is over, we just remove it. Or we think that that is box 1. Then you go to the next chapter thinking that from that box 1, nothing will be used in the next chapter. That is how our mindset was till class 10th. Now that will not work. All the boxes are connected here. Whatever you learn in kinematics will be used in laws of motion, will be used in work by energy, everything will be used in rigid body, everything will be used in fluid mechanics. Everything is connected. Okay. So always be open about it. All right, next. Okay, the angle is not given. This distance and that distance. This distance is y. This distance is x. Okay. You have a block over here. Block of mass m. Coefficient of friction is mu. Okay. Find out क्यों भाई? Camera is on भाई. Oshik is not able to see me. Everybody else can see me. Yeah, Oshik. ये ले. I think once in a while I should ask you guys also to switch on your webcam. All of you sit in a chair and a table to study. Is there anyone who is like lying on a bed कि ऐसे लेटे हुए हैं भाई देख रहे हैं movie types with popcorn? It's not a news channel, okay? Don't watch it like a news. All right, find out the total work done. Total work done is what? Work done by all the forces, one by one, and add them up. Total work done by all forces on mass M. When you're adding the work dones, by one force with the other force, do you have to use vector addition you have to do, or you can add them like numbers? When you're adding work done by one force to the work done by the other force, you need to use vector addition, or you can add them like numbers. Everyone. Correct. You don't need to take any components. That's the best part. You can add them like numbers. So find out, everyone. Angle is not given, Oshik. Not given. But x and y are given. If you want to find angle, tan of theta is y by x. Type in your answer, Kshitij, what you got. Complex. If it is complex, probably that is not correct. Work done by the time the mass from the top, it reaches the bottom. What is the work done by gravity, everyone? When it reaches from the top to the bottom, what is the work done by gravity? Work done by gravity. Gravity is direction is vertically down. Okay. So do I know the displacement in the direction of mg? Y is a displacement, y. Okay. So work done by gravity is mgy. You can see here I have used force into displacement in the direction of force. Earlier, previous case, just before this, what we have used? We have used force in the direction of displacement into displacement. Okay, because displacement was given along the incline, but over here in this particular case, in this particular case, displacement is given in the direction of mg directly. It is given. Fine. So I can use mgy. Okay. I hope everybody understood. Now work done by friction is what? Friction force is in this direction. Mu times normal reaction. Okay. Normal reaction is what? You can see by doing the force balancing, we have done it so many times. Mg cos theta. Okay. Mg cos theta, assuming theta is there, but I have to replace theta later on. So normal reaction is mg cos theta. So force of friction, mu mg cos theta, work done is negative of mu mg cos theta into that distance, right? Which is what? Root over x square plus y square. Isn't it? Now cos theta is what in terms of x and y? Anyone? Cos theta is x divided by root over x square plus y square. By base into hypotenuse, right? So this and that, they're gone. So you'll get minus of mu mgx. This is the work done by the friction. Okay, work done by the friction. The total work done, see normal reaction work done is how much? Everyone? Work done by normal is what? Because normal reaction is another force acting on it. It is 0. Okay, work done by the normal reaction is 0. So only these two work dones are there. So I can say that mg times y minus mu x is the total work done on this block by all the forces. Got it? Let's clear, right? I'll go to the next question now. Everyone? Okay. So the next question. All right, so I'll just write down here. Everyone, so there is a block like this. There's a block of mass m, okay? And it is tied with a thread, all right? This is a thread and you are applying, it is tied with a thread and the mass is accelerating down with g by 4 acceleration. Acceleration is g by 4. Okay, you need to tell me work done by the tension in 1 second. Not 1 second. Let me give you root 20 seconds. How much is the work done? Take GS 10. Work done by the tension will be positive or negative? Positive or negative, everyone? Will be negative. Work done by the tension will be negative because tension will always pull the block along the string. Tension is upwards, gravity is downwards. Did you find the value of tension? First, you need to find the tension because force into displacement is a work done. Work done by the tension is tension into displacement. If you don't know the tension, how will you find the work done by it? So mg minus t is equal to m into g by 4. So tension is 3 mg by 4. This is the tension. Okay. And the displacement S is ut plus half at square. Can I use this here? This formula can I use? I can use it because acceleration is constant. U is initial velocity, which is 0. So half acceleration is g by 4 into t square. This, okay. G is 10, or let's keep it as 5g by 2. So work done by the tension is negative. Why negative? Tension is upwards. Minus of 5 mg by 3 mg by 4 into 5g by 2. Anybody got this? This is minus of 3 by 8 into 5m into 100. So 4 to 25, 125 into 3. कितना हो गया 125 into 3? 375. 375 by 2 times m. This is the answer. Okay. M is not given. Clear? All right. Next, write down. You have write down. You have these questions. I could not take the image, so I'm just reading it from the screen. A body of mass 6 kg, 6 kg mass is there. It is under a force that causes displacement like this. It is following this law. S equal to t square by 4, where t is the time. You need to find the work done by the force in 2 seconds. I'll write down the options, then I'll take the poll. Start doing it. Should I put the poll? RI poll. Yellow. All right, I'm ending it up now. This is what you guys have selected. Acha, by the way, how many of you use calculus here? Is it a constant acceleration or not? Is this a case of constant acceleration? Acceleration is constant or not? How do you know it is constant? Displacement is 1 by 4 t square. So velocity is what? Derivative of this. So which is t by 2. Acceleration is derivative of velocity, which is 1 by 2. So 1 by 2 meter per second square. This is the acceleration. So acceleration is constant. So force is also constant. Force is equal to mass times acceleration. 6 into this, that is 3 Newton. 3 Newton is the force. And in 2 seconds, what will be the displacement? Simply use this formula. Displacement S is t square by 4. 2 square by 4 is 1 meters. So the work done is F into S, which is 3 joules. That is option D. Got it? Right? Now, if the force is given as okay. Let's take a variable force example. Write down. First, let us finish this. Then we'll proceed with other questions. Work done by a spring. Spring force is a constant force or a variable force? Everyone, is it a constant or a variable force? It is a variable force. So suppose you have a spring. Draw a spring with me. Here is a spring. Spring constant is given to you. Spring constant is K. All right. Okay. Right now, the extension in the spring is X1. Extension in the spring is X1. And you are pulling the spring in this direction. Initial extension is there. X1 is the initial extension. So because of your pull, the spring gets elongated. So because of your pull, the spring constant K, the elongation becomes X2. Okay. In this process, when initial extension was X1 and the final extension is X2, in this process, what is the work done by the spring? All of you do that. Find out the work done by the spring, how much it is. Will spring do a positive work or a negative work? First tell me that. Yes, from x1 to x2. Will spring do a positive work or a negative work? Why negative? Depends. If x2 is more than x1, that's what I'm asking. It is being pulled. Work done by the spring, I'm asking. Spring force is in which direction? Spring applies force in this direction. Displacement of the point of application of the force is that direction. So they are in opposite direction. Force this way, point of application of force is this way. So they are in opposite direction always. Work done will be negative. How much it is, everyone? Should I do it? At any point in time, assume that at any point in time, assume that the extension in the spring is x. So force will be what? If extension at any moment is x, the force of the spring will be kx. Okay. Now you're displacing it by, this is a variable force. This is a variable force. So you have to integrate it. So you assume that you're displacing by little amount of dx. For that small dx, you're assuming force is kx only. So the small amount of work done by the spring, by the time it gets displaced by small distance dx, is it kx dx? Is this correct? Force is kx, displacement is dx. Is this expression correct? All of you tell me. Won't there be a negative? No. Force is, force is kx. Displacement is dx. So force into dx, force into displacement is the work done, right? So that is why kx into dx. Now will it be positive or negative? Positive, negative? Positive कैसे भाई? Displacement you are having in this direction, spring is pulling you backwards. So how can it be positive? It is negative. Spring is trying to pull you back, right? Total work done will be integral of this. X goes from x1 to x2. So W is equal to minus of k by 2 x square goes from x1 to x2. So the work done by this spring is half k x1 square minus of half k x2 square. Everybody understood this? Quickly type in. All of you type in. Second last step. Integral hai. This is integral x square by 2. Then I'm putting upper limit minus lower limit. So that's why it comes. Minus is there. So x2 square minus x1 square becomes x1 square minus x2. Clear? Okay. Now tell me one thing. All of you tell me one thing. If initially it is extended by x1, okay, listen here, listen. All of you, listen here. At t equal to 0, initially extension of x1, then you are compressed by x1, then extend by x1, you're back to the initial stage. Then you extend by x2. So rather than, listen here, rather than going from x1 extension to x2 extension, what you did was from x1 extension, you compressed it by x1, then again extended by x1, and then you went to extension of x2. So work done in this case, will it be different or will it remain same? Initially extended by x1, then you compressed it, then extended it, and then went to x2. So initial and final points are same, but in between you did all this circus. Will it be same? How? How? Don't answer mathematically. Physically, you will say that, okay, this situation is similar to that because of this, and hence it will be same. How will you answer it physically? No. In the end, it doesn't matter. You're just, you know what is the outcome, so you're debating. You have to prove it. Displacement is same, so what? That doesn't guarantee anything. If you take a block like this, if you take a block, you go this way and then come back to the same point, work done by friction will be 0. Huh? If you take a block like this, when you go this side, friction is this way, negative work done. When you come back, friction is this way. So again, negative work done. Although displacement is 0, work done by friction is not 0. Is there any lag? I don't think there is any lag, Ansh. It is probably at your end, some net issue. What I'm saying is, if you follow these steps, extension of x1, then compression of x1, extension by x1, and then extension by x2. Rather than going from extension x1 to extension x2, in between you did this, but initial and final points are same. Will the work done be same? The answer is yes, it will be same. But why? I don't know. You're still answering it mathematically. All of you, listen to me. Listen to me the way I was expecting your answer. Listen here. Okay. Now, initial extension is x1. Initial extension is x1. When you go from x1, when you're going from x1 till its natural length, the work done will be positive or negative by this spring. When you're going from extension x1 to the natural length, by this spring, work done will be positive or negative? Spring is extended. You're going to its natural length. Work done is positive. Spring is anyway pulling you and you're following the spring. Work done is positive. Okay. Now, when you are compressing it further from natural length to x1, work done is positive or negative? नहीं समझ रहे हो तुम लोग. What I'm trying to say here. See, that is the reason. That is the problem. You guys are thinking it is mathematics. It is not. Okay, you need to think. You need to visualize. So there is an extension in the spring. Now spring in its natural length. Spring was trying to pull this way. You have displaced it this much. It is positive work done in the direction of force only. Displacement is there. Now you're compressing it. Which direction the spring force was when you're compressing it by x1? Spring force was in this way, but you're compressing that way. So this is positive work done. This is negative work done. Both are same. From extension to 0, the magnitude of work done is same as from 0 to compression of x1. Similar situation in opposite direction. So net, this positive, this negative will add up to 0. You haven't done anything. No work is done. When you're from extension of x1 to the compression of x1, first you did positive work, then you did negative work, net 0. Okay. And then what you're doing, you're going back to this position. What you do, you're now going to the natural length. Work done will be positive. From natural length to the extension of x1, the work done is negative. Again, positive, negative, 0. So basically, from extension of x1 to compression of x1, the work done is how much? Work done is 0. Okay. And similarly, compression of x1 to extension of x1, again work done is 0. So it does not matter. From x1 you have compressed it and then again back to the extension x1. The net work done is 0 only. Okay. So hence in between what you do doesn't matter. The work done by the spring will be half k x1 square minus half k x2 square. Okay. And with this discussion, another very important thing has come up. Write down this expression again. Work done is half k x1 square minus half k x2 square. Now, do I need to tell you whether x1 and x2 are compression or extension? Basically, what I'm saying is case number 1 is from compression of 5 centimeter to extension of 10 centimeter. Then case number 2, extension of 5 centimeter to extension of 10 centimeter. Will the work done by the spring in these two cases will be same or different? What is the difference? Initial condition for first one is compression of 5 centimeter. The second one, initial condition is extension of 5 centimeter. Will the work done be same or different in two cases? Will it be same or not? चलो पोल करते हैं. Will the work done be same? Will the work done be same? Work done will be same or not? Okay. So still I can see 50-50%. See, you don't want to think. It is not that you cannot think. You don't want to think. That is the problem. Again, listen here. You can see here what is written. Compression of 5 centimeter to the extension of 5 centimeter. Compression of 5 centimeter to the extension of 5 centimeter, work done is 0. So between 5 centimeter compression to 5 centimeter extension, no work is done. It is 0. So whether you start from compression of 5 centimeter or extension of 5 centimeter, if final is same, the work done is same. Okay. So the conclusion is it does not matter whether x1 is compression or extension or x2 is compression or extension. All you have to see how much deviation from its natural length initially is x1. Whether it is compression or extension does not matter. All I have to hear, it is 5 centimeter away from the natural length. Whether it is 5 centimeter compression or extension, I don't want to. X2 is similarly final, extension or compression. Okay, so work done is independent of whether x1 and x2 are compression or extension. All you have to find out from initially how much it is deviated and finally how much it is deviated. Everyone clear? Everyone is clear? Then we'll take a break. Otherwise, let me know what is the doubt. Quickly. Nothing. Ansh, x1 and x2, you don't need to worry whether they are compression or extension. That is what I was saying. Okay. Clear? All right. So right now it is 6:10. We will meet in 15 minutes. All of you come back in time. Okay, are you able to hear me? Am I audible? Not audible. All right, so let us proceed. We have till now only talked about the definition of the work. Okay. And after defining what is work, we have found out the work for various cases, right? But you can as well define something random, like, you can define, let's say, some parameter and say that that parameter is a square divided by velocity cube dot with force, dot product with force. And you just find out that variable for various scenarios. Same thing we have done. We have defined work done as force into displacement in the direction of the force. And then we have just found out the value of the work done for various cases. It's like I have randomly defined the formula and then I have started finding the values for different cases. So till now, whatever we have done is not useful because it is no longer, it is not connected to the real world. You have hypothetically defined the formula for the work. Okay. Now, first time we are trying to connect the definition of work with something which we observe or something which is realistic. Okay. So basically I am talking about here work energy theorem. Write down. Okay, now tell me, what is energy? Energy is what? Then we'll proceed further. What it is? You might have heard about the definition of energy in class 9th or 10th. What it is? Something that enables force. That's very complicated definition. Anything else? Ability to do work. Okay. Ability to do work. That seems a little simpler definition. Or capacity to do work. Right? So basically, the work done is your capacity. Okay. It is capacity or ability to do work. Doesn't mean that work is done. If energy is there, doesn't mean that work is done. No, right? It is just that, I have energy to do something. I may or may not be doing it. It is as simple as that. But is energy required to do the work? Definitely it is required. If you do not have energy, you cannot do the work. That is like basic. It is a requirement to have energy. It is like you need to purchase book to read it. But just because you have hundreds of books piled up in your house, does it mean that you have studied them? No. Most of the time, it is people fooling themselves only. They just pile up so many books and none of the book is done properly. Okay, so it is just like you are accumulating energy, but you're not doing anything about it. Having said that, a book is required if you want to read something or if you want to learn something. Similarly, energy is required, but it is just an ability to do the work. You may or may not have done the work. Okay, in mechanics, there are many kinds of energies. Like for example, heat energy, then electrical energy, nuclear energy, chemical energy, many kinds of energies are there. But we are talking about mechanics. Okay, in mechanics, only two types of energies we are talking about. Write down mechanical energy. Can you guess what are these energies? What are these two kinds of energies? Any guesses? Correct. Kinetic and potential. Write down kinetic energy and potential energy. Okay. Now, kinetic energy is the energy due to movement. Okay. Potential energy is due to position, shape, size, and everything else. Okay. So energy which is there because of the movement is kinetic energy. Energy that is there because just the way it is, just the way the position, location, shape, and everything else it is. Because of that, if there is energy, that is potential energy. Okay. So the expression of kinetic energy is straightforward, which you have learned earlier itself. Kinetic energy, I am sure all of you have seen it earlier, half m into v square. Okay, this is the kinetic energy. So potential energy is something which we will learn in the next class. Right now, our focus is kinetic energy and the work. Fine. So let us see how kinetic energy is connected to the work done. All right. Now, for a constant force, write down for a constant force, constant net force, acceleration is constant, and hence I can write down v square is equal to u square plus 2as. Now this displacement is in the direction of acceleration, right? Because when we use this in projectile motion, you remember, when we take along x-axis, displacement along x-axis, acceleration along x-axis. Similarly along y-axis. So everything is along the acceleration and displacement should be in the same direction. Okay, so this s is in the direction of a. So if you want to write in a vector form, you can take a dot product between a and s like this. Fine. Now multiply both sides with half of m. Everyone do this. Half mv square equal to half m u square plus m into a dot s. Now I can simplify it further. I can write down it as m into a dot s is equal to half m v square minus half m u square. Now tell me, what is m into a? What is m into a? Force or net force? It is force, one of the forces, or total force? Only one of them. Net force, correct. Net force. Net force is equal to mass m acceleration, right? That is what Newton's second law is. M into a is not equal to just one force. M into A is sum of all the forces. Okay. So sum of all the forces dot with S is final kinetic energy, let's say K2 minus initial kinetic energy K1. Okay. Sum of all the forces can be written as F1 plus F2 and so on. Dot with S is K2 minus K1. Now, you can expand it further. F1 dot S plus F2 dot S and so on is equal to K2 minus K1. Now, F1 dot S is what? What is F1 dot S? It's very vague. If you just say work, doesn't mean anything. What is F1 dot S? Everyone. Work done by one of the forces, work done by F1. Okay. So F2 dot S is work done by F2. So basically left hand side is work done by all the forces. Sum of all the work done. Total work done. If you find out total work done on a mass, this will be equal to K2 minus K1. This will be equal to K2 minus K1. Okay. This expression is the expression for the work energy theorem. Okay. Right now we are using this for one mass at a time. Right? We are having only one mass, half mv square, half mu square, K final kinetic energy minus initial kinetic energy. Can I use this work energy theorem for two masses together? Okay, two masses are there together. Can I use this? Okay, so the expression will be, you can use it, work done by all the forces on mass 1 is K2 minus K1 for M1, or I can write it like this. Work done by all the forces on M1 is half M1 V square minus half M1 U square. Work done by all the forces on mass 2 is half M2 V square minus half M1 U square. Okay. When you add up, you'll get work done on mass M1 plus work done on mass M2 is equal to half M1. Their final velocity will be different. M1 V1 U1 V2 U2. M1 V1 square plus half M2 V2 square minus of half M1 U1 square plus half M2 U2 square. See, right hand side is what? Right hand side is sum of all the kinetic energies. Finally, kinetic energy of M1 plus kinetic energy of M2 finally minus sum of all kinetic energies initially. Kinetic energy of M1 plus kinetic energy of M2 initially. Now, the problem with the left hand side is that there will be some internal forces work done also. Because when we find the work done, we only take care of the external forces. We don't find out that, the van der Waals force between the two atoms, they'll be pulling each other, atoms will be moving here and there inside the material. Because all the internal forces, work done will become zero when it add up. I haven't proved it, but it is zero. Similarly, when you add up the work done on mass M1 plus work done on mass M2, when you add up the force between M1 and M2, okay, the force between M1 and M2, their work done will add up to 0. So this will be work done by all the external forces on both the masses together is change in kinetic energy for both the masses together. Okay, so in case you want to use work energy theorem for system of 2-3 masses, you can use this, but it is rarely used like this. Most of the time, we will be using this form, one mass at a time. We'll take one mass, find out the work done on it, total work done, that will be equal to change in kinetic energy. Now, how this formula is useful? Can anyone tell me? Work done is equal to K2 minus K1. How will this be useful to find what? Everyone. To find energy for the work. Okay, what else? What else? Can I find the final velocity? I can find the final velocity also. Work done is equal to change in kinetic energy. So I can find out the final velocity also. But can you find out the final velocity by other means also? You can find out the acceleration, and you can find out by using acceleration, you can find the velocity. So multiple ways you can get the velocity, but you will understand the power of this equation only when you solve some of the questions. Okay, so let us see. This one will be used mostly in the advanced level question, JEE Advanced, in which you have to use work energy theorem for multiple masses at a time. You will not be comfortable with this straight away. So first, start applying on one mass at a time, then only you can go to this level. Now, what is the assumption till now? When we have used work done, when we have defined the work energy theorem, what is the assumption here? Everyone, look at it, tell me. The assumption is what? What kind of force it is? Constant force. We have used constant force. What if force is variable? Will then the work energy theorem is valid or not? For that, you write down kinetic energy is equal to half mv square. Okay. Mass, you assume constant. Okay. Mass, if it is constant. Then if you differentiate the kinetic energy, dk by dt, you will get what? Half m 2v dv by dt. This is what you get. Hold on, Ansh, I'm in between something. You want me to do this? Hold on. So 2 and 2 gone. Now this will be what? This will be m into dv by dt into v. This will be dk by dt, right? So dk by dt is equal to m into a. Velocity can be written as ds by dt. Okay, so dt is gone. So dk is m into a is what? Net force. So net force dot ds, or I can say f dot ds. Net force is, let's say, f is dk. When you integrate, dk will become integral of f dot ds. What is the right hand side? This is what, everyone? What is this? This is the work done. Okay. Here, the force need not be constant. Even for the variable force, integral F dot ds, this is from initial kinetic energy to the final kinetic energy. You will get integral of F dot ds. This is equal to the work done. It is equal to K2 minus K1. So it does not matter whether the force is constant or a variable force. The work done will always be equal to change in kinetic energy. When I say work done is change in kinetic energy, I'm saying work done by all the forces. Even you have to include work done by gravity and spring. Later on, you'll be taking them as potential energy. That we'll discuss later on. Right now, work done, when you find out, you need to find out the total work done. All the forces, find out the work done one by one and add them up. Total work done will be equal to change in kinetic energy for a mass. Is this very clear to everyone? Type in quickly. All of you, I'm waiting for all of you. I'll start taking names otherwise and ask you to explain also. Quickly. Clear, right? Okay. Okay. Fine. Previous slide. Previous slide. This one. Oro Chawla. You're not Ornav. You want me to say Oro. Oro told me to say Oro, not Ornav. Is NAV silent? Oro? Okay. Done? कौन था भाई? Grover? Ansh Grover? Fine? All right. Okay, so let's see. Couple of numericals we'll take up on work energy theorem also. That is what was the today's agenda. We will do these two things. Nothing else. Let us see. I want you to use work energy theorem to solve these questions. Do not start using other ways of solving. Coefficient of friction is mu. Okay. You are applying a force from this direction. Force is F. Okay. This block get displaced by a distance of S. Okay. You need to find out the initial velocity is U. U is the initial velocity with which it is moving. You need to find out the final velocity of this mass when it has displaced by a distance of S. Done? Okay. Kshitij is done. Others? Find out the work done by all the forces, add them up, and equate it to change in kinetic energy. What else you have to do? You know how to find the work done. One by one, you find out, add them up. Should I solve or wait, everyone? Oshik, you got it? Gurman? Pradyun? Okay. Okay. Listen here. You need to find work done by all the forces first. Work done by the force. How much it is? This is mg. There is a normal reaction also. Multiple forces are acting on it. There is a friction as well. Mu times normal reaction. हाँ भाई बताओ. Arnav, what is the work done by the force? Arnav तो यहाँ नहीं है. Arya, what is the work done by the force? F. Tell me quick. Work done by the force F over here. How much? Arya, F into S. Correct. Now, Oro, what is the work done by the gravity? 0. Work done by the normal reaction? 0. Okay. Somebody left the moment I start taking names. कौन गया भाई? Who left? Who left? Anyways, Gurman, work done by the friction. How much it is? Oro started investigating. Huh? You do your work. Work done by friction. How much? Gurman. Gurman answered. Minus of mu n into S. What is n? N minus mg is equal to 0. So n is equal to mg. All right. So this will be equal to minus of mu mg into S. Okay. So total work done is what? Is there any other force which can do work? Any other force which can do work? No, right? So total work done is F into S plus 0 plus 0 minus mu mgs. This should be equal to change in kinetic energy. Final kinetic energy half mv square minus half m u square. That's all. Okay. So you will get m into v square equals to m into u square plus fs 2 times fs minus mu mgs, or v you will get it as u square minus mu g minus f by m times s to the power half. Anybody got this answer? 2 factor of 2. Okay, great. Do you think it is difficult? All you have to do is to find out these values one by one and just find out the total work done, equate it to changing kinetic energy. Nothing else you have to do. Straightforward, isn't it? Free body diagram, entire mechanics is free body diagram. Okay, if you are not comfortable with free body diagram, physics, I can't leave the physics then. Free body diagram, you have no option but to get comfortable with. Okay, I can't say anything more. Very comfy. You don't know. You have to solve at least 200 questions to say that you are comfortable with free body diagram, because we have been solving. Let me tell you, you might be thinking that we are solving very difficult questions. They are nothing. They are school level questions. Okay, I'm not able to solve very difficult question with you because the way I'm getting response. If you are able to solve difficult ones, then I'll give more difficult ones. If you struggle with these basic ones, I can't move forward. Getting you? Sorry, getting me? So you have to do your homework. Then only you'll get comfortable with all of this. Okay, anyways, focus here. This is, let's say, X. Okay, there is a block over here. Block is a point mass, of course, M. This is mu. Coefficient of friction is mu. You need to find out what will be the velocity when it reaches the bottommost part over here. It has been now 4 to 5 months. I haven't eaten pizza. Every few weeks, I used to have one big pizza. Do you guys had pizza for a couple of months now, or you also like not eating anything out? You can order homemade. Yeah, I have bought the cheese I have bought, the oven pan on which the pizza can be made, and trying to make homemade, but I don't think it will be as good as Domino's or thing. Okay, Arabi had one already. At least it is a pizza. Pizza can be, you can call a bread a pizza. If you say that that is at least a pizza, anything can be pizza. Your chapati is a pizza. Okay, done. Bakwas kara lo bas. When I am talking nonsense, everybody is interested. Yeah, yeah, you can do this and that. When I'm asking what is the answer, everybody is quiet. Gossip. Arnav is saying ignore everyone. I'm solving. Sure. Let's see if Arnav can get it. Arnav, don't call everybody stupid. That's so bad. Okay, anyone got near to the answer? Anyone? Almost. Arabi is still eating out. Find out the work done. Total work done is change in kinetic energy. Change in kinetic energy is total work done. Total work done is change in kinetic energy. Okay, both ways. Okay, I can see some of you got the answer. Very good. Fine. Listen here now. Free body diagram, like always. Mg cos theta, perpendicular to incline, along the incline mg sin theta, normal reaction, friction. Any other force? No. Which all forces are doing work? Which all forces doing work? Normal reaction, is it doing work? Is normal reaction doing work? No. Even mg cos theta doesn't do any work. Then who is doing work? Friction and mg sin theta. Okay. So mg sin theta work done is mg sin theta multiplied by this distance. This distance is how much? Inclined plane distance is what? Everyone? X cos theta, x sin theta, x by cos theta, x divided by cos theta. Its hypotenuse, how can it be less than the base? So mgx tan theta. Can I say this is also the work done by the gravity, entire gravity force? This is the work done. Can I say that? All of you? Can I say that total work done by the gravity is this? By work done by mg cos theta is 0. Work done by mg sin theta is this. So total work done by gravity is that. Are you getting it? This is the work done by gravity. This should also be equal to mg into displacement in the direction of mg. This much is the displacement in the direction of gravity. Can you tell me how much it is? This is how much? If this is x, this is theta, this is what? This will be x tan theta only, right? So whether you write this way or that way, you get the same answer. So mg into x tan theta, same thing. Okay. So work done by the gravity is this. Work done by the friction, how much? Minus, it is a negative work done. Minus of mu times normal reaction is mg cos theta. Normal reaction into displacement is x by cos theta. So total work done is how much? Total work done is mu mg into x. This is the work done by the friction. So total work done is this plus that. So I can say that mg x tan theta, I can take mg x common. mg x tan theta minus mu. This is the work done, total work done. This should be equal to final kinetic energy half mv square minus initial kinetic energy 0. So m gone. So velocity is root over 2gx tan theta minus mu. Clearly mu should be less than tan theta. If mu is more than tan theta, velocity will be imaginary. In fact, the block won't even move. If friction is more than, coefficient of friction is more than tan theta, block will remain there only for that theta. Okay, let's proceed. You have a block of mass m. This is a block of mass m. This angle is theta. Okay. And yes, this distance is x. This is smooth. The horizontal surface has coefficient of friction mu. Okay. So what will happen? It will come down sliding very fast and hit the surface. Surface, there is a friction. So after some time, it will stop horizontal distance. Some horizontal distance, it will stop. You need to find out how much distance it will cover before coming to rest. This distance, S, before coming to rest, how much it is? Anyone got the answer? Okay, Kshitij got it. And yes, that's correct. This is your initial point 1. This is your final point 2. The best part is both initial and final kinetic energies are 0. Initially it is at rest, finally also at rest. So net work done should be equal to what? Total work done will be 0. Change in kinetic energy is 0 because K1, K2 both are 0. So from here till this point, let's say this point is 3. From 1 to 3, gravity is doing work. Any other force that is doing work other than gravity? Between 1 and 3, any other force that is doing work other than gravity? Type in quickly. Friction is 0. No. No other force is doing work other than gravity. Normal relation perpendicular to the plane. Okay. Only two forces are there, normal relation and gravity. So work done by gravity is m into g, and displacement in the direction of force is this, which is x tan theta. Now between 3 and 2, is gravity doing work? From 3, point number 3 onwards, is gravity doing work? Is there a displacement in the direction of gravity? Bhai likho, type in. No, right? Gravity is not doing work from 3 onwards. Then who is doing work from point 3 onwards? Who is doing work? Friction. How much? How much? Minus of mu times normal reaction into S. What is normal reaction from 3 point onwards? It is equal to mg. From 3 point, normal reaction over here is mg cos theta. Over here it is mg only. So the total work done, mgx tan theta minus mu mg into S, this should be equal to 0 because K2 and K1 both are 0, here at rest, here also at rest. So S is equal to x tan theta divided by mu. Okay. And it clearly, you in physics, after getting answer also, you can visualize whether it is correct or not. If mu becomes 0, how much should be the distance? If friction is not there, it keep on moving. Newton's first law, S will be infinite. And that's how the answer is. Okay. All right, we have 15 minutes. We can solve a couple of, I have 3 questions, but I will be, okay. All right, let us take this one first. See, many questions can be made. All right. And now you guys are well equipped to solve any questions from this chapter. But if there is if there are terms like momentum, impulse, and potential energy, you can leave those questions. Other than that, you can solve any question. Anyway, I'll write it at the end also. Right now, let's focus on this question. You are applying a force F that is equal to K into X. Okay, it changes with X, but angle with horizontal is constant, theta. This is mass M. Okay, you need to find out velocity of block when it's about to leave leave the ground. Okay. Find out. X is the distance covered. X is a distance covered in this direction. Initially force is 0. As it moves horizontally, the X keeps increasing. That is the X. What is the condition for the block to leave the surface? What is the condition? Condition is normal reaction becoming 0. Every time something leaves the surface, normal reaction should become 0, right? If you take component of force, this way it is kx. You keep on doing. Those who have the confidence, please continue. This one is kx sine theta. This is mg. And you have a normal reaction. I could have given friction also, but kept it simpler. So I can remove this force. Okay. Now, condition I have to find out. First, I'll get the normal reaction. N plus kx sine theta minus mg is equal to 0. So normal reaction is mg minus kx sine theta. So when normal reaction becomes 0, the object lifts off the surface. So x is equal to mg by k sine theta. Okay, so at this distance x, the block will leave the surface. Now how to get the velocity? How to get the velocity of the block? Work energy theorem. Simple. So total work done is equal to half mv square minus initial kinetic energy, which is anyway 0. W is what? How to get the value of W? Anyone? How to get W? Which force is doing work? Out of all these forces, which one is doing work? Kx cos theta is doing work. Is it a constant force or a variable force? Varying force, you have to use integral. Okay, so kx cos theta dx integral, where x goes from 0 to this value. You have to find out what is the velocity at that value, right? K sine theta. So this one will be k cos theta into x square by 2. So mg by k sine theta, the whole square. This is the work done. Equate this to half mv square and you will get the value of velocity. Everybody understood? Is this thing clear to everyone? Quickly tell me. I have 2 more questions, but I think I can only take up 1 more. Why integral? Because the integral, because force is variable force. How can you say force into displacement? F dot dx you have to do, right? This one you can say advanced, the easy advanced question. Okay, the easy advanced questions will be like this. There are many difficult type of questions also. Okay, clear, right? I can take 1 more question if time permits. We can take another one also. Here is the question, all of you. You have a block of mass m hanging with a string of length L. Length L, mass m. Okay, bhai? Now I am somehow giving it a velocity of u. What will happen? It will swing, right? It will swing. And let us say the maximum angle it swings is theta. So it will go like this and then come back. Go like that, then come back. It becomes a pendulum. Okay. You need to find out what is the angle theta. Find out. What is the angle theta? What's the maximum value of theta for which it swings to the extreme, velocity becomes 0 and then returns? The mass is a point mass. The disclaimer I have already given at the first chapter only. Even if elephant is there, you assume it is a point. U is the initial velocity. U is the initial velocity perpendicular to the length. Will it be a circular motion or not? Are you able to see that? Yes, final velocity is 0. It will move in a circle. It is an arc of a circle. Simply you have to use work done by all the forces is final kinetic energy minus initial kinetic energy. Don't have to do anything else. Kshitij got something which, correct. Kshitij got correct. Everybody else who is doing work on the mass, what are the forces? Mg is one force, then tension, right? Is tension doing work? Tension doing work throughout or not? Everyone. Tension is doing work. Okay. Right now, what is the angle between tension and the small displacement the mass makes? What is the angle between tension and small displacement over here? 90 degree. Right now, over here, tension and displacement, again 90 degree. Every time the tension force makes 90 degree with the displacement. So the work done by the tension is 0. Okay, got it? So only work is done by the gravity. Along the line of gravity, how much distance it has moved up? Vertically, you have to find out, right? Along the direction of the force, the displacement is this much. This is the displacement. How much it is? Anyone? How much it is? This distance is what? You can see this is a 90 degree. This is L, this is theta. So this will be L cos theta. From point 1 to point 2, total length is L. So this is L minus L cos theta. So L into 1 minus cos theta. This is the distance vertically. So the work done by the gravity will be positive or negative? Everyone? Work done by the gravity, positive, negative? Negative, how much? Minus of mg into this distance, L into 1 minus cos theta. No other force is doing work, so this you have to substitute here. So work done by the gravity, which is minus of mgl 1 minus cos theta, this is equal to K2 0 minus K1 half m into u square, right? And from here, the value of cos theta, let me directly write down, cos theta will come out to be 1 minus u square by 2gl. Theta is cos inverse of that. Everybody understood? Type in quickly. Everybody understood? Okay. So basically, the other two questions, I'll give you homework. Homework for today. Today only, before going to sleep, you can solve many questions, but these two questions you must solve. So I'll just draw the diagram for it and just explain to you what it is. Then you can try your own. No, you can't leave right now. Hold on. Okay, so there's a block at a height of h from an incline that Okay, that is not given actually. You don't need it because it is smooth surface. Work done by gravity will be mgh only. This is mass m. Okay, it takes a circular arc. After this point, it goes in a circular arc. This angle, this total angle is 2 theta. This is theta. This is also theta. Okay, it is a symmetrical circular arc about that vertical line. And after this point, it leaves the surface. Okay, and it becomes a projectile motion once it leaves it. Okay, you need to find out the maximum height of the projectile, h max, and let me do one thing. Let's say this is the ground. Okay, the ground is at a depth of h by 2. So this projectile is falling on the ground. I'm just making it a little bit more involved so that you spend some time. If you know how to solve it already, then you'll not learn anything. You have to struggle a little bit. This essentially is range R. So you have to find the range of the projectile also. Everybody understood this question? You can say advanced level. Okay. Everybody understood this question? There is one more question. This is question number 1 for homework. If there is any doubt with respect to this question, you can ask in the group also. Okay. Next question. Hold on. I can't repeat multiple times. Hold on. Let me finish up this, then I'll repeat the previous one. You have a situation like this. There is a mass M. There is a spring that is connected from the wall. This is spring constant K. There is a thread from here to there. This mass is 2m. Okay. Now, at t equal to 0, spring in its natural length. Spring extension is 0, natural length. Okay. You need to find out maximum extension of spring when you leave the system. Okay, I think this one I don't need to explain further. Let me go back to the previous one. I'll explain that again. This is clear, right? This question is clear, everyone? Type in quickly. Clear, right? Okay, over here I'm explaining again. There is a mass kept on the inclined plane at a height h. It is left. It will slide down. Take a circular arc. Circular arc subtends at angle 2 theta at the center. Then it leaves a circular arc, becomes a projectile. You need to find out the maximum height from the ground. This is h max. Okay, how much is the maximum height and what is the range of the projectile? Angle of the base is not given. This angle is given. All surfaces are smooth. I don't want to complicate it. Getting it? So you have to do this today, and that's it from my side. We will meet next week, same time. Bye for now.